Imagine for a moment looking at the sky on any given night in September. Most of the time, what we see is familiar. The usual constellations, the planets shining on their predictable course, and, if we're lucky, a shooting star fleetingly crossing by. But this month, the story is different. Astronomers and amateurs who watch the firmament have noticed an unusual parade of visitors. Large asteroids, small rocks that get too close, a new comet just peeking through, and an interstellar traveler making its way towards Mars. It seems as if the cosmos has decided to remind us that we are never alone in the vast darkness. September is not just any month, it's a busy month in the sky. Before we continue exploring these mysteries, allow me an invitation. If you like stories of the universe, told calmly, designed for learning while you rest, this channel is your place. Subscribing is a simple way to join us on each cosmic journey. Also, in the comments, tell us from which city or country you are listening. Each response is like a star lighting up in our community, a constellation of voices that unites around curiosity and science. That is our call to action, a bridge between the sky and those who observe it from Earth. And now, let's return to the mystery. What is happening in September of 2025 that makes it so special? The headlines have already captured the attention of millions. An asteroid the size of a building that passed safely, but very close. Another tiny one, barely a rock of a few meters, that grazed the lunar orbit. A new comet, discovered just a few days ago, that extends its greenish tail in the firmament. And, as if that weren't enough, an interstellar visitor that does not belong to our solar system and is approaching Mars on a trajectory that will never be repeated. This is not science fiction. It is the reality of our sky this month, a silent and cosmic spectacle unfolding above our heads. Think about the magnitude of all this. For centuries, comets and asteroids were seen as omens. They were signs of misfortune for those who did not understand their nature. Today, we know that they do not bring messages from gods, but they do contain valuable secrets, stories written in ice and rock from the origin of stellar systems. And in September, several of those messengers have decided to cross our path. It is as if the universe has opened a window to show us fragments of its past and its diversity. The first protagonist is the asteroid 2025 FA22, with an estimated size between 130 and almost 300 meters. It was enough to attract press headlines around the world. Its passage on September 18th posed no real danger, but it awakened the imagination. After all, a rock of that size would be capable of causing devastation if it impacted our planet. Calculations by NASA and the European Space Agency reassured everyone. It would pass at a distance more than double the lunar orbit, safe but close in astronomical terms. That contrast between the tranquility of science and the magnitude of the object captured global attention. Just a few days before, on September 15th, another much smaller visitor approached Earth. It was designated 2025 RJ2, a rock of just a few meters. It passed so close that it grazed the moon's orbit. An object of that size does not represent a threat to life on Earth. Upon entering the atmosphere, it would disintegrate like a fireball, perhaps with a striking flash, but nothing more. However, its detection and tracking demonstrated the precision of current monitoring systems. Even the tiniest cosmic visitors do not go unnoticed. While astronomers were discussing these passes, another discovery added excitement: the comet C2025 R2 SWAN. It was found on September 11th thanks to the SWAN instrument of the SOHO satellite. Its initial brightness placed it near the limit of visibility with binoculars, and it is already anticipated that in October it will be possible to observe it with greater clarity. It has a distinctive tail and a greenish glow that connects it with the tradition of famous comets. Each discovery like this is like opening a new chapter of cosmic history, one that astronomers and amateurs will read together. And without a doubt, the main protagonist of September is the interstellar visitor 3I Atlas. It is the third confirmed object to come from outside our solar system, after Oumuamua in 2017 and Borisov in 2019. Atlas does not follow the rules of common comets. Its irregular brightness, its early release of water, its greenish coma, and its chemical anomalies make it a living mystery. Right now, it is approaching Mars, and although it will not touch the red planet, its trajectory will take it close enough to be studied in great detail. It is an unrepeatable spectacle. It will never return, and we will never see exactly this visitor again. The extraordinary thing about this September is not a single event, but the coincidence of all of them. In a matter of weeks, we have seen asteroids of different sizes, a new comet, and a unique interstellar object parade by. It is as if the universe had decided to remind us that it is alive, in constant motion, and that our Earth is just a momentary stop on a cosmic highway where travelers of all kinds circulate. That is the idea I want to leave at the end of this first block. September of 2025 is not just another month. It is a month in which the sky was filled with cosmic bodies, a busy month that will remain in the memory of astronomy. September of 2025 is already marked on the astronomy calendar as a particularly busy month. What is usually a relatively stable sky in terms of space news became a dynamic scene, with headlines changing week by week. For skywatchers, it was like attending an unexpected parade where each visitor brought their own story and their own mysteries. This block seeks to provide a general overview of that phenomenon. Why, suddenly, it seems that the universe threw several objects at us at once, and what this means in a broader context. The first thing to clarify is that the cosmos is always full of objects that pass close to Earth. Small asteroids cross our orbit constantly, and comets travel elongated paths that bring them closer to the Sun regularly. However, not all of them reach a sufficient magnitude to be newsworthy. Most of the time, these bodies pass unnoticed, too distant, too small, or too faint in brightness to represent anything more than a technical note in observatory bulletins. What made September special was the coincidence of several relevant events in the same time window. Astronomers do not experience it as a complete surprise. They know that the detection of near-Earth objects has increased exponentially thanks to technology. Automatic tracking telescopes, like Pan-STARRS in Hawaii, the Atlas in Chile, or the new facilities being prepared in different parts of the planet, scan large portions of the sky every night. That means that today we identify bodies that in the past would have passed without anyone noticing them. Therefore, part of the feeling of a busy sky comes not so much from there being more objects, but from the fact that we now see them better. Modern astronomy is like turning on a spotlight on a stage that was previously half dark. What was always there is revealed with greater clarity. Even so, it is still striking that in less than a month, we have the asteroid FA22, the small RJ2, the Comet SWAN, and the interstellar visitor Atlas. Each one, separately, would have been enough to generate expectation. Together, they form a powerful narrative. An asteroid that recalls potential risks, another that demonstrates the precision of our warning systems, a comet that offers us a spectacle, and a visitor that defies traditional categories. All in the same month, all sharing headlines. The feeling of busyness is also reinforced by how the media transmit this news. The general public does not distinguish between a 100-meter asteroid and a 4-meter one, nor between a periodic comet and a newly discovered one. What they perceive is a succession of announcements that seem to pile up. An asteroid will pass today. Another body is approaching tomorrow. A new comet is discovered. An interstellar object is detected. That creates the impression that the cosmos has suddenly become more active, when in reality, what is happening is that we are paying more attention and communicating more effectively. Now, what does it imply that so many objects are concentrated in September? From a statistical point of view, it is not impossible. The orbits of asteroids and comets are not synchronized with our human calendars. The coincidence of several passes in the same month is the product of chance on astronomical timescales. For Earth, revolving around the Sun, it is like crossing paths with several passers-by on a busy corner. It does not mean that there is a hidden pattern, but it does offer the opportunity to reflect on the dynamic nature of the solar system. In fact, this concurrence becomes a pedagogical lesson. It allows for a real-time comparison of different types of bodies. Astronomers can contrast the properties of FA22, a large asteroid, with those of RJ2, a tiny rock. They can observe how a newly discovered comet like SWAN behaves and, at the same time, closely follow an interstellar visitor that will never return. It is like having an open cosmic laboratory in the same month with varied and unique samples. For the general public, this month becomes a reminder that we live in a universe in motion. There is no such thing as a motionless sky. What seems static on our quiet nights is actually a gigantic choreography of bodies that orbit, fall, cross, and continue their millennial trajectories. The difference is that in September, that choreography became visible in a more dramatic way. If we look back, there are precedents for months in which several phenomena coincided. In 1994, for example, the impact of the fragments of Comet Shoemaker-Levy on Jupiter coincided with close passes of medium-sized asteroids. In 2013, the Chelyabinsk asteroid entered the atmosphere of Russia the same year that another asteroid, DA-14, passed close to Earth with a few days of difference. These events generate headlines and the impression of unusual activity, although they are part of the statistical normality of the cosmos. September of 2025 joins that list, with the difference that now the media coverage and detection capability are much greater. Some wonder if this concurrence could be related to external factors, such as the position of the solar system in the galaxy or major gravitational disturbances. The answer, according to scientists, is that there is no evidence of such a pattern. Asteroids follow trajectories that respond to the gravity of the Sun and nearby planets. Comets, for their part, are guided by elliptical orbits that bring them back to the inner system every certain number of years, or in the case of non-periodic ones, only once in millions of years. And interstellar objects, like Atlas, follow hyperbolic trajectories that lead them beyond our star without returning. Each one responds to known laws. What changes is our perception. In conclusion, September has become a powerful reminder of how varied the cosmos is. It is not just a month with more activity than usual, but a demonstration of how the progress of science allows us to observe and understand more. The sky was always busy. What happens is that now we notice it with greater clarity. And that is the magic of this block, understanding that the universe is not fuller in September than it was before, but it is more visible, closer to our attention, more present in our conversations. To understand why September of 2025 is so fascinating in astronomical terms, it is worth stopping for a moment and clarifying something fundamental. What is the difference between an asteroid and a comet? They are words that we often hear in the news, and that are sometimes used almost as synonyms, but in reality, they describe two very different types of bodies that travel through space with their own histories and characteristics. Imagine asteroids as the leftover building blocks of the solar system. When our cosmic neighborhood was formed more than 4.5 billion years ago, fragments of rock and metal were left over that never managed to join together to form planets. Those fragments remained orbiting the Sun, mainly in the region known as the asteroid belt, between Mars and Jupiter. Millions of objects live there, from rocks a few meters across to bodies hundreds of kilometers in diameter. Asteroids are, in essence, space rocks. Some contain iron and nickel, others are more carbonaceous, but they all share the characteristic of having no atmosphere or visible activity. When we see them from Earth, they appear as points of light that move slowly, without tails or special glows. Comets, on the other hand, are much more theatrical travelers. They are also remnants of the birth of the solar system, but their composition is different. Instead of being made mostly of rock and metal, comets are balls of ice mixed with dust and organic compounds. We could describe them as dirty snowballs, although the metaphor falls short because they contain complex chemicals, from frozen water to carbon monoxide, carbon dioxide, methane, and ammonia. The key is that, as they approach the Sun, those ices begin to sublimate. That is, they go from a solid to a gaseous state without becoming liquid. That process releases large amounts of gas and dust into space, forming the characteristic bright hair or coma, and the tails that can extend for millions of kilometers. That is why comets are so spectacular. They are not simple points of light, but living brushstrokes that change shape and color as they advance. This essential difference explains why September offers us such rich contrasts. On the one hand, we have asteroids like FA-22 and RJ-2, rocks that travel in silence, without a visual spectacle, but loaded with importance due to the potential impact they could have on Earth. On the other hand, we have comets like SWAN and the Interstellar Atlas, bodies that show activity, that develop tails, that arouse fascination both among scientists and of the public. Observing them in the same month is like seeing actors from different plays parade on the same stage. There is another interesting aspect. While asteroids tend to stay in relatively stable orbits around the Sun, comets usually have much more elongated trajectories. Some return every few years, like Halley's Comet, famous for appearing approximately every 76 years. Others take thousands of years to return, and there are those that enter the solar system only once and never come back, as is the case with many non-periodic comets. And then there are the even rarer visitors, interstellar comets like 3I Atlas, which were not even formed with our Sun, but around other stars, and which cross our neighborhood by pure chance. Differentiating between asteroids and comets is also key to planetary security. A large asteroid that impacted Earth would have devastating consequences, as demonstrated by the Chicxulub event 66 million years ago, which contributed to the extinction of the dinosaurs. In contrast, most of the comets we see do not represent a direct threat, because they usually pass at safe distances. However, their behavior is more difficult to predict. A comet can fragment, release more gas than expected, or slightly alter its trajectory by expelling jets of material. That unpredictability makes them subjects of permanent study. The scientific interest in both types of bodies is enormous. Asteroids are time capsules that preserve information about the formation of the planets. Some recent missions, such as NASA's OSIRIS-REx, which brought back samples from the asteroid Bennu, seek precisely to understand their composition and history. Comets, for their part, are even more valuable because they contain organic compounds that could have played a role in the origin of life. A widely considered theory suggests that a good part of the water and basic ingredients for biology on Earth arrived thanks to comet impacts in the first millions of years of our planet. In September of 2025, by observing asteroids and comets in the same time frame, we have the opportunity to appreciate that contrast. Asteroids remind us of the solidity, permanence, and latent risk of impacts. Comets bring us spectacle, complex chemistry, and the possibility of better understanding the origins of life. Both are messengers from the remote past, and both raise questions that we have not yet been able to fully answer. For those who listen to this story with the intention of resting, perhaps the best image is to think of the sky as a cosmic river. In that river float stones and fragments that we call asteroids, solid and immutable. But from time to time, that river carries blocks of ice that, upon melting, shine with flashes of gas and dust. Those are the comets. September has been like a special stretch of that river, in which both types of travelers passed before our eyes almost at the same time, reminding us that the universe is not static, but a living and constantly transforming stage. On September 18th, 2025, all eyes were on a rocky visitor that earned headlines in media around the world. The asteroid designated 2025 FA22. For many, its name may sound like a simple combination of letters and numbers, but behind that code lies a cosmic rock of impressive dimensions and with a story worth telling. FA22 is an asteroid classified as near Earth, which means that its orbit brings it from time to distances that, in astronomical terms, are considered close. Its estimated size ranges between 130 and almost 300 meters in diameter, which places it in the category of large asteroids. To have a clear idea, a body of that size is equivalent to a building of between 40 and 90 floors, traveling through space at tens of thousands of kilometers per hour. The interest in FA22 is not because it represented an immediate danger, but precisely because of the contrast between its size and the safety of its trajectory. Orbital calculations made by NASA and the European Space Agency showed that it would pass at more than twice the distance that separates the Earth from the Moon, which is equivalent to about 800,000 kilometers. In human terms, that figure may sound enormous, but on astronomical scales, it is a close encounter. Therefore, although scientists insisted that there was no cause for alarm, the public could not help but feel a chill. After all, imagining a rock hundreds of meters across, passing at only a couple of lunar distances, is enough to ignite the imagination. This type of news reminds us of the importance of planetary surveillance. In the past, humanity had no way of knowing when an asteroid was approaching. Today, thanks to a global network of telescopes, we can detect these bodies in advance and calculate their trajectories with great precision. In the case of FA22, the data were so clear that astronomers could guarantee that there would be no impact. However, the simple fact that this asteroid is on the list of monitored objects shows that surveillance is not a luxury, but a necessity. Asteroids of this size, if they were to collide with Earth, could cause a regional disaster of unimaginable proportions. Although they would not extinguish humanity or cause a global winter like the impact that ended the dinosaurs, they could destroy entire cities or entire regions. The energy released in an impact of a body of more than 100 meters would be equivalent to thousands of megatons of explosives, something that far exceeds any weapon created by humans. Therefore, every time an object like FA22 approaches, the scientific community takes the opportunity to remind the public why it is crucial to invest in planetary defense programs. But beyond fear, the passage of FA22 also offers a unique opportunity for science. Each close encounter allows astronomers to study the characteristics of these bodies in more detail. With telescopes from Earth, light curves can be obtained that reveal the asteroid's rotation speed, its approximate shape, and even clues about its composition. In some cases, planetary radars are used, such as the one that operated in Arecibo before its collapse, or the one that now operates in Goldstone, to obtain high-resolution images of the surface. Although FA-22 passed too far for a detailed radar, it did leave useful data that will be added to the growing catalog of near-Earth objects. The cultural interest that these asteroids arouse is not new. Since humanity understood that past extinctions were linked to impacts, every news about a nearby body awakens both curiosity and fear. Headlines usually highlight the dimensions by comparing them to football stadiums or skyscrapers, because we need familiar reference points to imagine the magnitude. In the case of FA-22, there was talk of a space skyscraper, and that mental image spread quickly. It is important, however, to remain calm and understand the real scale of the risks. Most of the large asteroids that cross Earth's orbit are already catalogued, and their trajectories are monitored years in advance. That means that the scenario of a surprise collision with a body hundreds of meters across is becoming less and less likely. Current tracking programs, along with future telescopes such as the Vera C. Rubin Observatory in Chile, will further improve this security. FA-22 on its September visit was not only a reminder of the risks, but also of the progress made. It was observed, followed, and predicted with enough anticipation for the world to know that there was no danger. Instead of generating panic, it gave us the opportunity to reflect on our place in the cosmos and on the need to remain vigilant. For those who looked at the sky those days, FA-22 was invisible to the naked eye, but its story resonated just the same. It was not necessary to see the rock with one's own eyes to feel the impact of its presence. It was enough to imagine its size, its speed, and the dance of gravity that guided it to pass close to us. That act of imagination is also an act of science, because astronomy is built as much with data as with the human capacity to visualize the invisible. Ultimately, the passage of asteroid 2025, FA-22, in September of 2025 will not be remembered for a disaster, but for the tranquility with which it could be anticipated. It is a triumph of modern science, a demonstration of how we have learned to read the sky and to coexist with the risks that living in a solar system full of moving rocks implies. And above all, it is a reminder that, although we are surrounded by potential threats, we also have the intelligence and technology necessary to understand and face them. If the asteroid FA-22 reminded us of the magnitude of what a body of hundreds of meters means, September 15th, 2025 was the turn of a much smaller visitor, but no less interesting for that. This is the asteroid designated 2025 RJ2, unlike FA-22, whose size could be compared to a skyscraper. RJ2 was just a rock between 4 and 6 meters in diameter, something more similar to the size of a large van or a small bus. And yet, its passage managed to attract the attention of astronomers and the press because it approached Earth at a much smaller distance, even closer than the Moon. To put what happened into perspective, it is worth remembering that the average distance between the Earth and the Moon is 384,000 kilometers. The asteroid RJ2 passed at a fraction of that distance, which makes it a close encounter in every sense of the word. In other words, if the Moon were a sentinel guarding our orbit, this small visitor dared to cross under its guard. It did so without posing any risk, but enough to remind us that the space near Earth is full of small fragments in constant motion. The notable thing about RJ2 was not its size, Because asteroids of a few meters enter the Earth's atmosphere frequently, most of the time disintegrating without leaving more than a luminous flash in the sky. What was really striking was the precision with which it could be detected, followed, and catalogued. Just a few decades ago, an object like this would have passed unnoticed. Today, thanks to astronomical surveillance networks, we know of its existence, we calculate its trajectory, and we can inform the public in real time. That speaks not only of technological advances, but also of a change in our relationship with the cosmos. Imagine what an impact from an object like RJ2 would mean. It would not cause global destruction or even regional. Upon entering the atmosphere, friction with the air would disintegrate it in a matter of seconds. The energy released would produce a fireball visible for tens or even hundreds of kilometers. Depending on the place of impact, it could be heard as a loud sonic boom, but nothing more. The most would be some minor damage if the fragments reached the ground in populated areas, which is highly unlikely. In fact, every year the Earth receives impacts of this type, and most go unnoticed, occurring over oceans or unpopulated areas. And yet, the passage of RJ2 generated interest. That demonstrates something important. Our perception of asteroids does not depend only on their size, but on their proximity. A small rock that passes extremely close can cause more headlines than a large rock that passes farther away. Proximity has an immediate emotional impact. It reminds us that we are in the middle of a constant flow of objects that cross our planet's orbit. Earth does not travel alone around the sun. It does so in the company of thousands of fragments that from time to time get too close. The fascinating thing is that this small visitor also offers opportunities for science. Although we cannot study it with the same precision as a larger asteroid, the simple fact of following its orbit adds information to the global catalogs of near-Earth objects. With each new record, we improve our ability to predict future encounters and to understand the dynamics of these rocks. Even the smallest ones provide valuable data, as if they were tiny pieces of an immense puzzle that describes the history of the solar system. Another interesting aspect is how these events serve to train alert systems. Astronomers take advantage of encounters like that of RJ2 to test their detection, calculation, and communication methods. Each object discovered confirms that current programs work, but also reveals areas where they can be improved. It is a continuous learning process, driven by the need to be prepared not only for small rocks, but also for large ones that may pose a real risk in the future. If we think about it in poetic terms, RJ2 was like a spark in the darkness, a reminder that the sky is alive and in motion. It was not seen with the naked eye. It did not leave bright tails like a comet, nor did it represent a spectacle for millions of people. And yet, its presence was significant. It was a lesson in humility. Even the smallest rocks travel at speeds that defy imagination, and their impact energy, although limited, reminds us that the universe is dynamic and never still. Compared to FA22, RJ2 seems insignificant. But that comparison is misleading. Both are part of the same picture, that of a busy September in which different types of bodies crossed our path. Together, they show us the breadth of the spectrum of cosmic visitors, from giants that evoke fear to tiny travelers that barely graze our attention. Each one plays its part in reminding us of the need to observe, monitor, and learn. Ultimately, the passage of RJ2 will not be remembered for its size or its impact, but for its proximity. It was a discreet, almost invisible visitor, but one that reinforced the feeling that September of 2025 was a special month. A month in which the sky was filled with cosmic bodies of all kinds, and in which humanity could look up with a mixture of wonder and gratitude, aware that we live in a neighborhood full of movement and stories to be told. The almost simultaneous presence of the asteroid FA22 and the tiny RJ2 in the same month invites us to reflect on something inevitable. What would happen if one of these bodies, large or small, were to impact the Earth? Thinking about that possibility may sound unsettling, but it is also a way to understand why astronomers dedicate so many resources to studying and monitoring these objects. The scenarios are very different depending on the size, and September of 2025 offers us the perfect opportunity to contrast them. Let's start with the case of a large asteroid like FA22. With an estimated diameter of between 130 and almost 300 meters, an impact of that size would release a colossal amount of energy. To put it in perspective, a 200-meter body could release an energy equivalent to tens of thousands of megatons of TNT. That figure is difficult to imagine, but it is enough to remember that the most powerful nuclear bomb ever tested by humans, the so-called Tsar Bomba, had a power of 50 megatons. An asteroid like FA22 would multiply that energy thousands of times. The effect of such an impact would depend largely on the location of the collision. If it occurred in an ocean, it would generate gigantic tsunamis capable of devastating coastlines thousands of kilometers away. If it happened on land, it could raise entire cities, raise clouds of dust that would darken the sky, and alter the climate for months or even years. It would not be a global extinction event like the one that ended the dinosaurs, because for that, a body several kilometers in diameter would be needed. But it would be a regional or continental disaster with enormous consequences for millions of people. Now let's think about the opposite extreme, a small asteroid like RJ2, just 4 to 6 meters across. Its impact would be much more modest. Upon entering the atmosphere, friction with the air would largely disintegrate it before it reached the ground. The result would be a fireball visible over a wide area, perhaps accompanied by a sonic boom that would break windows or scare those who witnessed it. The most famous example of an event of this type occurred in 2013 in Chelyabinsk, Russia, when an object about 20 meters in diameter entered the atmosphere. The shock wave broke glass throughout the city and caused minor injuries to more than 1,000 people, although no one lost their life directly from the impact. RJ2, being even smaller, would have generated a luminous spectacle, but would hardly have caused major damage. The difference between the two scenarios is crucial for planetary defense. The large ones, like FA22, are rare but much more dangerous. The small ones, like RJ2, are frequent and almost always harmless. The Earth receives tons of space dust and smaller fragments every day that burn up in the atmosphere without us noticing. A rock the size of RJ2 can appear several times a year in different parts of the world, and most of the time it becomes a bright meteor that surprises those who observe it. In contrast, an impact from a body hundreds of meters across occurs at intervals of tens of thousands of years, but its consequences are much more serious. That is why detection programs prioritize large asteroids. The goal is to make sure that none of them take us by surprise. At the same time, the small ones play another role. They are useful as training. Every time one like RJ2 approaches, astronomers test their systems, adjust models, and confirm that the tools work. In a way, the small ones are like natural drills that help us prepare for the big ones. There is also a philosophical aspect to this comparison. Thinking about FA22 reminds us of our vulnerability to cosmic forces that exceed our ability to control. It forces us to recognize that the Earth is not an isolated bubble, but a planet in a dynamic environment where rocks circulate that could, in theory, change the course of history. Thinking about RJ2, on the other hand, reminds us of the everyday nature of these encounters. It shows us that we live on a planet that constantly receives minor visitors, that is part of an endless river of cosmic fragments. One awakens fear for its magnitude. The other awakens wonder for its frequency. Both, however, have something in common. They force us to look up. Every time the passage of an asteroid is announced, whether large or small, millions of people look up to the sky again, even if only symbolically. That keeps the link between humanity and the cosmos alive, a link that we often forget in the midst of daily life. Thus, September gave us a unique contrast. FA22 reminded us of what is at stake if we ever face a real planetary defense challenge. RJ2 reminded us that small encounters are part of our planet's day-to-day life. Together, they painted a complete picture, a sky in constant motion, full of risks and wonders, that we must continue to observe with patience and respect. While the asteroids were grabbing attention for their size and proximity, another protagonist was emerging in the September 2025 sky, a newly discovered comet named C2025 R2 SWAN. Its story began quietly, almost like a surprise that the cosmos decided to reveal at once. On September 11th, an amateur astronomer, Vladimir Bezubly, analyzed images from the SWAN instrument installed on the SOHO satellite, and noticed something out of the ordinary. In the midst of the patterns of known stars appeared a diffuse point with the characteristics of a comet. That detection would mark the beginning of a new chapter in the already busy month. The name of the comet tells us a lot about it. The letter C indicates that it's a non-periodic comet. That is, it does not have a short return cycle known as some famous comets have, for example, Halley. The number 2025 indicates the year of discovery. The letter R corresponds to the fortnight of the calendar in which it was detected, in this case, the first half of September. And finally, the number 2 places it as the second comet announced in that period. The acronym SWAN is due to the instrument that revealed it, the Solar Wind Anisotropes. This device, on board the Solar and Heliospheric Observatory, SOHO, has allowed the discovery of numerous comets over the years, becoming a key tool for astronomy. The interesting thing about SWAN is that it is not a telescope designed to search for comets. Its main function is to study the interaction between the solar wind and hydrogen in space. However, that same ability makes it an accidental detector of comets, because the atmospheres of these bodies usually contain hydrogen that becomes visible in the images. Thus, the satellite that observes the Sun also ends up revealing distant visitors. In this case, the discovery was possible thanks to the careful analysis of the images and the trained eye of an amateur who knew how to recognize something different. It is a reminder that science does not always depend on gigantic laboratories. Sometimes, patience and individual curiosity open new windows to the cosmos. After the initial detection, observatories around the world began to point towards the new coordinate. In a matter of days, Comet C2025 R2 SWAN went from being an anonymous finding to becoming an object of study. It was confirmed that its apparent magnitude was around plus 6.9, which means that it was at the limit of what is visible with binoculars in dark skies. It was not an obvious spectacle for anyone looking at the sky, but it was bright enough for those who sought it to find it. That difference is important. Large comets that become visible to the naked eye are rare, but every comet discovered adds valuable data to our understanding of how these icy bodies behave. The news of the discovery generated enthusiasm in the astronomical community. It is not every day that a new comet appears, and even less so in a month in which there was already so much celestial activity. Its discovery reinforced the feeling that September was full of surprises, as if the universe had set out to offer us a festival of visitors. While FA22 and RJ2 Reminded of the risks of asteroids, SWAN offered the promise of a more visual spectacle in the following weeks. The discovery also highlighted the importance of international collaboration. Once announced, professional and amateur astronomers from different countries began to share observations, calculate orbits, and predict how the comet would evolve as it approached the Sun. That dynamic reflects the modern way in which astronomy works, as a collective effort, where thousands of eyes and telescopes around the world work together to track a visitor. In that sense, C. 2025 R2 SWAN became not only an object of study, but also a meeting point for the astronomical community. The context of the discovery also deserves attention. It occurred just a few days after the headlines about FA22 and RJ2, which contributed to the public receiving it with greater interest. The media, which already had the audience's attention on the sky, found in SWAN another piece to narrate the story of the busy September. And although its initial brightness did not promise a spectacle to the naked eye, its mere existence added richness to the narrative. A huge asteroid, a tiny rock, and now a newly arrived comet. It was as if each type of celestial body had gathered on the same temporal stage. For those who follow the sky out of passion, the discovery was especially exciting because it offered the possibility of observing it with binoculars or small telescopes. The idea of pointing an instrument towards the exact place and finding a newly catalogued comet there adds a personal dimension to the phenomenon. It is no longer just a piece of data read in a headline, but a direct experience. It is looking with one's own eyes, a body that travels from the most distant regions of the solar system, carrying within it secrets of billions of years. The discovery of SWAN also reminds us of something fundamental. The sky always holds surprises. Despite technological advances, satellites, and automated detection networks, there is still room for unexpected discoveries, and that keeps the essence of astronomy alive, which is not only a science of data and numbers, but also of discoveries that generate wonder. Each new comet that appears is an invitation to stop and contemplate, to feel the connection between our small daily life and the gigantic processes that occur in the universe. In short, September 11th, 2025 will be recorded as the day a new actor appeared on the stage of the busiest month. C. 2025 R2 SWAN arrived unannounced, without an initial spectacle, but loaded with meaning. It is a reminder that the universe is full of travelers who go unnoticed until someone finds them. And it is also a gift, an opportunity to learn more about comets, to observe their characteristics, and to enjoy the ephemeral beauty of their passage. After its discovery on September 11th, the comet C. 2025 R2 SWAN began to attract increasing attention. It is not every day that a new comet appears in our skies, and even less so in a month already loaded with cosmic visitors. What makes SWAN special is not only its early detection, but also the characteristics that define it and make it an object worthy of observation and study. In its first days of tracking, astronomers calculated that its apparent magnitude was around plus 6.9. That means it is not visible to the naked eye, but it is accessible to binoculars and small telescopes under dark skies. It is like a gift for amateurs who know that part of the excitement is in looking for it, finding it, and contemplating its faint glow. In a way, that difficulty adds value. It is not an obvious spectacle for anyone, but a prize for those who take the time to look. One of the most commented characteristics is its greenish color. That tone, already observed in the first images, comes from diatomic carbon molecules, which, when excited by solar radiation, emit a characteristic green glow. It is the same chemistry that has given other famous comets their mysterious aura, and that makes SWAN a visually attractive object. Green in the night sky is not common, unlike the blue of young stars or the yellowish-white of planets. The green of a comet adds a unique contrast, as if it were a cosmic lantern traveling in silence. The beginning of a tail has also been observed, although still weak compared to what is expected for October. The tails of comets are formed when the heat of the sun causes the sublimation of their ices. The gas and dust released expand into space and are pushed by radiation and the solar wind, forming structures that can extend for millions of kilometers. In the case of SWAN, calculations suggest that it will develop a more noticeable tail as it approaches its perihelion. For now, the first flashes of that structure are enough to excite observers. In orbital terms, C2025 R2 SWAN is a non-periodic comet. That means that its trajectory is so elongated that it will probably pass through the inner solar system only once before returning to distant regions or even being lost forever in interstellar space. Its perihelion, the closest point to the Sun, will occur on October 29, 2025. That will be the moment when its activity intensifies and hopefully its brightness increases enough to make it more visible even without instruments. There are no guarantees. Comets are unpredictable. Some disintegrate before reaching perihelion, others surprise with a sudden increase in brightness. That uncertainty is part of the appeal. The date of its closest approach to Earth will be October 19th, when it will pass at about 39 million kilometers. That is, approximately 26 times the distance of the Moon. It may seem far, but on cosmic scales, it is relatively close. Enough for its tail, if it develops fully, to offer a spectacle worthy of follow-up from Earth. In the southern hemisphere, better visibility is expected in the first few days, although in October it can also be observed from the northern hemisphere at appropriate times. Comets like SWAN are not only a visual spectacle, they are also scientific objects of great value. Studying their composition and behavior allows us to better understand how the solar system was formed. These icy bodies are time capsules, remnants of the primordial cloud of gas and dust that gave rise to the planets. Analyzing the gases they release is equivalent to reading messages from billions of years ago. In that sense, SWAN is not just a curious visitor. It is a messenger that brings information from the depths of time. Another relevant aspect is that its discovery was due to an instrument designed to study the solar wind. That connects it with the idea that astronomy is, to a large extent, a science of unexpected findings. We do not always look for comets when we find them. They often arise as additions, as hidden treasures in data collected for other purposes. That detail adds charm to SWAN. It was a fortuitous discovery, a reminder that the universe always has surprises hidden in unsuspected corners. For the amateurs who have followed it since its first nights, SWAN is already a small cultural phenomenon. Social networks are filled with photographs taken with homemade telescopes, with drawings that try to capture its color and shape, and with excited comments about its evolution. In an era when public attention tends to disperse quickly, a new comet has the ability to gather looks and generate community. Those who have observed it in its initial phases feel it almost as a personal discovery, as if they were part of the story of its arrival. In the grand framework of September of 2025, SWAN brings a different nuance to that of the asteroids and the interstellar visitor Atlas. It does not represent a threat, it is not a rock that approaches dangerously, nor a mystery of distant origin. It is a classic comet, with a tail and brightness, with color and spectacle. It is a reminder that the cosmos also knows how to be beautiful and generous, not just unsettling. While FA-22 raises questions about planetary defense and Atlas inspires philosophical reflections on stellar origin. SWAN simply invites us to look and enjoy. Thus, the Comet C 2025 R2 SWAN becomes another protagonist of the busy month. It is not the brightest or the most dangerous, but it is one of the most grateful for observation. In its weeks of visibility, it will allow us to connect with the millennial tradition of observing comets, that practice that has inspired myths, poems, and discoveries. Although in a few months it will disappear from our skies, its memory will remain as part of the September in which the universe decided to fill the firmament with visitors. When we think of the asteroids, comets, and interstellar objects that appear in our skies, we usually imagine scientists with large telescopes discovering them directly, almost as if they saw them with the naked eye. But the reality is much more complex, and at the same time, fascinating. The modern detection of these bodies is the result of a global network of instruments, computer programs, human teams, and even the participation of amateurs who, with their own telescopes and cameras, contribute to finding and following these messengers from space. The first key is to understand that the sky is immense. Observing it completely in search of small and fleeting objects would be an impossible task for a single person or a single observatory. For this reason, astronomers have developed automated systems that scan the sky every night. Telescopes like those of the Pan-STARRS program in Hawaii, or those of the Catalina Sky Survey System in Arizona, dedicate their nights to photographing large portions of the firmament. Then, powerful computers compare the images obtained with previous records. If a point of light appears that was not there before, and it also moves with respect to the background of stars, the system marks it as a candidate. The case of 3I Atlas is a good example of how this network works. It was detected by the Atlas system, whose acronym in English means Asteroid Terrestrial Impact Last Alert System. Its main function is not to look for exotic comets, but to protect us. It scans the sky in search of objects that could get too close to Earth. Thanks to its design, Atlas can detect fast-moving objects and send early alerts. That it has discovered an interstellar visitor is almost an ironic twist. A program designed for planetary defense ended up being the first to detect the strangest traveler of recent years. In the case of comets like C 2025 R2 SWAN, the story is different. Its discovery occurred thanks to an instrument designed to study the solar wind, and not specifically to hunt comets. The SWAN instrument on board the SOHO satellite monitors the ultraviolet light emitted by hydrogen. That light can reveal the presence of comets, because as they approach the sun, they release enormous amounts of hydrogen gas. Thus, a satellite that was monitoring the behavior of the sun ended up discovering a new celestial visitor. This is the essence of modern astronomy. Science finds more than it seeks, because the universe always manages to surprise us. Another fundamental component is international cooperation programs. Organizations such as the International Astronomical Union maintain catalogs and databases that are updated in real time. When a telescope detects a possible object, that information is shared with other observatories in a matter of hours. Thus, a finding in Hawaii can be confirmed from Chile or from Europe the same night. International collaboration is crucial, because the movement of an object can only be confirmed if it is observed from different points on the planet. It is like following the flight of an airplane from several control towers at the same time. Amateur astronomers also participate in this network. Today, thanks to technology, an enthusiast with a medium-sized telescope and a good CCD camera can contribute with observations of great value. Many times, these amateurs are the ones who provide continuous follow-up of comets and asteroids when the large observatories are busy with other projects. There are even community networks, such as the Association of Comet and Asteroid Observers, where people from different countries share their data, images, and calculations. Thus, detection is not only a task for experts, but a collective effort that connects thousands of people around the planet. But not everything depends on telescopes. Computers and software play a decisive role. The amount of data that observatories produce is gigantic. Every night, the telescopes dedicated to these searches generate millions of images and records. Processing them manually would be impossible. For this reason, specialized algorithms are used that are capable of comparing thousands of photographs in seconds. These programs identify patterns of movement and discard known objects, such as variable stars or artificial satellites. Only what is truly new and in motion is marked as a candidate. The rise of artificial intelligence has also reached astronomy. Today, programs based on machine learning help to distinguish between false positives and real discoveries. In some cases, these systems have identified objects that went unnoticed in the first human reviews. The machine does not replace the scientist, but it becomes an indispensable assistant that amplifies their capabilities. The public often wonders how it is possible that we discover such large objects hundreds of meters across just days before they pass close to Earth. The answer lies in the difficulty of the task. These bodies are dark, reflect little sunlight, and move fast. Detecting them requires the alignment of many factors: atmospheric conditions, availability of telescopes, well-functioning algorithms, and, sometimes, a little luck. The surprising thing is not that they sometimes arrive with little notice, but that we manage to find them at all in such an immense sky full of luminous distractions. Detection does not end with the initial discovery. Once a new object is located, a process called astrometry begins, which consists of measuring its precise position on successive nights. With these measurements, astronomers calculate its orbit. The more observations accumulate, the more exact the prediction of its future trajectory is. This is how it was determined, for example, that the comet SWAN will pass at its minimum distance on October 19th. Or that the asteroid FA-22 did not represent a real risk despite its size. Another key phase is spectroscopy, which allows for the analysis of the light reflected or emitted by the object. With this technique, scientists deduce what it is made of, whether it is rocky, metallic, or rich in ices. This information is vital to understand its origin and behavior. It is not the same a metallic asteroid, which could withstand an atmospheric impact, as a rocky and fragile one that would disintegrate before reaching the ground. Modern detection, then, is a complex network. Automatic observatories scan the sky. Space satellites find comets while looking at the sun. Computer programs analyze millions of data in seconds. International networks share information almost in real time, and amateurs with homemade telescopes contribute crucial pieces to the puzzle. All this joint effort makes it possible for us today to talk about comets and asteroids with a confidence that in past centuries would have seemed impossible. The most beautiful thing is that each detection is also a story of cooperation. When we say that a comet was discovered by a satellite, or that an asteroid was detected by a telescope, what we are really saying is that hundreds of people, technologies, and observatories around the world worked together in a coordinated manner to illuminate a small point in the vastness of the universe. And in this particular month, September of 2025, that global machinery has been more active than ever. Each alert of a new object has been like a bell that resonates in all corners of the planet, calling observers to pay attention, to look up, and to confirm what another eye in another place had already seen first. So far, we have talked about near-Earth asteroids and a newly discovered comet. But among all the visitors that gathered in September of 2025, there is one that shines with an incomparable mystery. It is not a body that returns periodically, nor a local rock that has emerged from the asteroid belt. We are talking about a true foreigner, an interstellar traveler who came from another stellar system. Its name is 3I Atlas, and since its detection, it has become the most studied and talked about object of the moment. The name 3I tells us that it is the third confirmed interstellar object in the history of astronomy. Before it, only two had been catalogued. The first was Oumuamua, discovered in 2017, and the second was the comet Borisov, detected in 2019. Atlas joins as the third, and its appearance confirms what many astronomers suspected. Our solar system is not an isolated bubble. Objects ejected from other systems travel through the galaxy, and from time to time one crosses our path. The second term of its name, Atlas, corresponds to the system of telescopes that discovered it. The Atlas program, whose acronym in English means Asteroid Terrestrial Impact Last Alert System, is based in Hawaii and is designed to detect objects that may pose a risk of collision with our planet. It was while fulfilling that mission that it detected this unusual traveler, which not only did not represent an immediate risk, but also showed an impossible orbit for a local body. The first observations revealed something surprising. The trajectory of Atlas did not correspond to an elliptical orbit around the Sun. Instead, it described a hyperbolic orbit, that is, an open curve that does not return. That data was decisive. Only an object that comes from interstellar space can show that kind of trajectory. Unlike a comet from the solar system, which always returns in long or short cycles, Atlas was simply crossing our cosmic neighborhood. It arrived, it let itself be seen, and it will continue on its way to other regions of the galaxy. The speed of this traveler also caught attention. By calculating its relative motion, astronomers estimated that it travels at more than 60 kilometers per second with respect to the Sun. That figure far exceeds the typical speed of comets that belong to our system. To have an idea, 60 kilometers per second means covering the distance from Lima to Cusco in less than 10 seconds, or going completely around the Earth in just 11 minutes. That speed confirms that it is not gravitationally bound to our Sun, but simply passes by like a stone thrown at high speed that will never be caught. Another intriguing aspect is its visual appearance. Unlike Oumuamua, which surprised with its elongated shape and the absence of a visible tail, Atlas does show characteristics of a comet. It has a bright coma, that is, a cloud of gas and dust that surrounds its nucleus, and it develops a tail that extends in the opposite direction to the Sun. But even in this, it is strange. Initial analyses indicated that its coma is richer in carbon dioxide than expected, and that its chemical spectrum presents unusual lines, including traces of nickel. These details have generated debates in the scientific community because they do not fully fit with what we know about typical comets. The combination of an interstellar trajectory, a dizzying speed, and chemical anomalies makes Atlas a fascinating object. For many astronomers, it is a unique opportunity to study material that was formed in another solar system, perhaps hundreds or thousands of light years away. Each particle of gas it releases is a testimony to processes that occurred in places we will never see directly. Observing it is like receiving a letter written millions of years ago from an unknown star. At the same time, its passage reminds us of the ephemeral nature of these opportunities. Atlas will not return. Once it crosses the solar system, it will continue on its way without looking back. That means that every night of observation counts, that every piece of data collected is unrepeatable. Scientists know this, and that is why telescopes on all continents have been mobilized to follow it. Space satellites, professional observatories, and amateur telescopes are contributing pieces to the puzzle, trying to understand as much as possible before it disappears from our sight. There is also the cultural and emotional dimension. Since its announcement, Atlas has aroused the interest of the general public. It is not uncommon to find headlines that compare it to Oumuamua, speculating on whether it could have an artificial origin. That possibility, although not supported by evidence, reflects our fascination with the unknown. Each interstellar visitor raises the inevitable question: what if it were not just a rock or a comet? What if behind its shape and movement there was something more? Although science is cautious and does not affirm such hypotheses, the simple fact that they arise shows how these objects activate the collective imagination. At this point in the narration, it is worth stopping for a moment and contemplating the magnitude of the event. It is not every day that we receive a visit from an interstellar object. In fact, until less than a decade ago, we had not confirmed any. Today, with Atlas, we have 3 in a very short period of time. That suggests that perhaps there are more than we thought, and that our solar system is regularly crossed by travelers from other stars. Simply, we now have the technology to see them. What distinguishes Atlas from the asteroids FA22 and RJ2, or from the comet SWAN, is precisely its interstellar character. The other objects are local, fruits of the dynamics of our own system. Atlas, on the other hand, is a reminder that we live in a populated galaxy, where stellar systems are not isolated, but share fragments ejected by collisions and gravitational processes. Each interstellar object we detect is a piece of that cosmic exchange, proof that the Milky Way is more dynamic and connected than we usually imagine. That is why the passage of 3I Atlas feels like a historical event, not only for what it reveals scientifically, but for what it symbolizes. It reminds us that we are not alone in the physical sense. Our solar system receives visitors who come from other stars. And although they are only icy rocks, their existence connects us with a much wider universe, full of stories that we are just beginning to hear. When astronomers began to study 3I Atlas in more detail, they soon realized that they were not dealing with a common comet. Its status as an interstellar object already made it special. But what really caught their attention were the anomalies detected in its composition and behavior. These unusual features have turned Atlas into a cosmic puzzle, one that we have not yet fully understood. One of the first surprises came from spectroscopic analyses. By observing the light emitted and reflected by the comet, scientists found an unusually high level of carbon dioxide. In the comets of our solar system, this gas is present, but in moderate proportions. In the case of Atlas, the amount detected was significantly higher than expected. This excess may have several explanations. One possibility is that it comes from a different formation environment, where carbon dioxide was more available in the primordial cloud that gave rise to its stellar system. Another possibility is that its nucleus preserves deep layers of ice that we rarely see in local comets, and that, upon sublimating, they reveal different compositions. The discovery of carbon dioxide is not just a chemical detail. It tells us that Atlas is not quite like the comets we know. Its composition reflects a different formation environment, perhaps in a colder stellar system or with a different chemistry. Studying it is equivalent to opening a window to conditions that do not exist in our neighborhood. It is like receiving a laboratory sample that comes from a distant planet. Each molecule tells a story about its origin. Another intriguing anomaly was the detection of traces of nickel in its spectrum. Nickel is a metal found in some meteorites, but seeing it in the atmosphere of an interstellar comet was unexpected. Its presence suggests that the nucleus of Atlas could contain metallic materials mixed with ices, something uncommon in local comets. This combination suggests violent formation processes where collisions or stellar explosions could have enriched its composition. Again, there is no single definitive answer, but the data breaks molds and raises new questions. The way its tail behaves has also given people something to talk about. Unlike the typical dust and gas tail of comets, that of Atlas showed irregular variations, as if it reacted more sensitively to the currents of the solar wind. Some astronomers noticed that it seemed to fragment into sections or show rapid changes in direction. This led to comparisons with Oumuamua, which also showed behavior that was difficult to explain with classic models. Although there is no evidence of anything unnatural, the fact that both Oumuamua and Atlas have shown anomalies has given rise to riskier hypotheses. Among those hypotheses is the idea that some interstellar objects might not be just natural fragments, but remnants of ancient technologies. It is a thought that science cannot confirm, but that it cannot discard without definitive proof either. The truth is that when an object behaves in an unusual way, our imagination is activated. And although astronomers prefer to look for natural explanations, they know that speculation is part of human curiosity. Another detail that surprised was the stability of its rotation. Many comets rotate chaotically, with wobbly axes and irregular periods. Atlas, on the other hand, showed a rotation period of around 16 hours, quite stable for an object that has traveled billions of years through interstellar space. That regularity is strange, because in theory, it should have suffered countless collisions and tensions that altered its spin. Some researchers suggest that it could have fragmented recently, revealing a younger and less altered nucleus. Others suggest that it is simply a traveler who has been lucky enough not to encounter too many obstacles on its way. The anomalies are not limited to its chemistry and rotation. There is also the fact that its coma formed earlier than expected, even when it was still at a great distance from the Sun. Normally, comets begin to show activity when they get close enough for the solar heat to sublimate their ices. Atlas, on the other hand, already exhibited a visible coma much earlier. This suggests that its surface contains extremely volatile compounds which sublimate at lower temperatures. That characteristic fits with the idea that it comes from a very different environment from ours, perhaps a stellar cloud rich in light compounds. Each of these anomalies, taken separately, could be explained within the margins of the possible, but together they draw a peculiar profile. Atlas does not quite fit into the categories we know. It is like a puzzle piece that seems to belong to another game, and it is that rarity that makes it so valuable. Studying it forces us to rethink our models of how comets form and evolve. It reminds us that what we consider normal is only a fragment of a much wider diversity that exists in the galaxy. Astronomers have stressed that the most important thing is to gather as much data as possible while it is still close. Once it moves away, it will be impossible to observe it in detail. That is why telescopes on the ground and in orbit have dedicated so much time to following it. Each image, each spectrum, each measurement of its brightness can reveal additional clues. It is like trying to read an ancient manuscript, of which we only have a few pages before it is lost forever. The public, for its part, has received this news with a mixture of fascination and mystery. Headlines about anomalies in an interstellar comet circulate quickly because they raise deep questions. Could there be life in other systems? Could these objects be carriers of materials that seed worlds? And what if, in the most extreme case, one of them were something more than just a natural fragment? Although science proceeds with caution, it is inevitable that these questions will take hold in the collective imagination. Thus, 3I Atlas becomes more than a fleeting visitor. Its anomalies transform it into a mirror where we project both our knowledge and our doubts. It is a reminder that no matter how much we advance in science, the universe always holds surprises that defy our categories. And each surprise drives us to look further, to ask more, and to accept that not everything is resolved. Every time astronomy encounters a strange object, the questions transcend the strictly scientific and delve into broader fields, where imagination and speculation mix with data. With 3I Atlas, precisely that happens. Its chemical anomalies, its stable rotation, and its interstellar origin have opened up a range of hypotheses that go from the natural and conservative to the risky and almost philosophical. In this block, we will explore how these explanations coexist, confront each other, and above all, feed the eternal debate about the possibility of life and technology beyond Earth. The first line of thought is the most prudent. For many astronomers, Atlas is nothing more than an exotic comet, a traveler that reflects the diversity of conditions in which these bodies can form in the galaxy. The Milky Way is home to hundreds of billions of stars, each with its own formation history, with its own mix of gases and dusts. It is not strange to imagine that from these differences, comets with different chemical characteristics are born. From this perspective, Atlas is simply a sample of that variety. Its high levels of carbon dioxide or the presence of nickel would be the signature of a particular origin environment, not an indication of something more. The second current is a little more daring, but still scientific. It posits that these interstellar objects could be carriers of essential materials for life. This is the old hypothesis of panspermia, which suggests that comets and asteroids can transport organic molecules through space and seed them on young planets. If Atlas comes from a stellar system where complex molecules already existed, its passage through the solar system is like a caravan transporting ingredients of life. Although there is no direct proof, we know that some local comets contain amino acids and simple organic compounds. Nothing prevents us from thinking that an interstellar object could be even richer in these substances. In that sense, Atlas could be a chemical messenger, a reminder that life could be distributed throughout the galaxy in the form of cosmic seeds. A third current goes further and connects Atlas with the eternal human yearning not to be alone. Here arise speculations about a possible artificial origin. Some remember the debate that surrounded Oumuamua, the first confirmed interstellar object, whose elongated shape and peculiar movement led a sector of the scientific community, led by astrophysicist Avi Loeb, to suggest that it could be a technological artifact. Although most astronomers did not accept that hypothesis, the discussion left its mark. Today, every time a new interstellar object appears, that idea resurfaces. In the case of Atlas, the detected anomalies have given fuel to those who wonder if it could be something more than a comet. The possibility that Atlas is artificial is not supported by concrete evidence, but by the combination of features that seem atypical. Its fragmented tail, its unexpected composition, and its stable rotation raise legitimate questions. After all, if an advanced civilization wanted to send probes into interstellar space, it is logical to think that they would camouflage themselves as natural bodies so as not to attract attention. That hypothesis borders on science fiction, but it also reflects a deeper concern that perhaps we are not the only ones who leave technological footprints in the galaxy. Beyond these speculations, the truth is that Atlas revives the conversation about how we prepare for the possibility of extraterrestrial life, not necessarily intelligent life, but any form of biology or advanced chemistry that we can detect in the cosmos. If each interstellar object brings with it unique information, we should take advantage of each encounter to look for clues. This includes not only measuring its orbit and brightness, but also analyzing its composition in as much detail as possible. In the future, when our technology allows it, we could even send probes to intercept these travelers, collect samples, and bring them back to Earth. Imagine the scientific value of having in our hands fragments of a foreign stellar system. The debate also touches on a philosophical level. Some wonder what it would mean if an object like Atlas were artificial. How would our vision of the universe change if we knew we were not alone? What would it imply for our culture, our religion, our politics? In a way, interstellar objects have become mirrors where we project both our curiosity and our fears. Each anomaly is interpreted according to our expectations and desires. For some, it is proof that life abounds. For others, it is a reminder of how much we do not know and how fragile we are in the cosmos. It is important to remember that science proceeds with caution. So far, there is no solid evidence to suggest that Atlas is artificial. What we have are data that reveal differences with what we know. But those differences are not necessarily extraordinary, but rather to be expected in an object that comes from another system. However, the border between the scientific and the speculative has never been rigid. Speculation feeds the imagination, and the imagination, in turn, drives new scientific questions. What cannot be denied is the cultural effect. Atlas has captured the attention of millions of people around the world. Videos, articles, and popular science programs discuss its characteristics. Some present it as a simple comet, others as an enigma, and still others as a possible artificial visitor. This diversity of interpretations demonstrates the power that these phenomena have to unite science and narrative. In an era saturated with earthly news, an interstellar object reminds us that there is a universe out there, full of mysteries that transcend us. In summary, 3I Atlas is not only an object of astronomical study, it is a catalyst for broader debates. It forces us to reflect on life, on technology, and on our place in the cosmos. Its anomalies become symbols, its hypotheses mirrors of our own search for meaning. And as we watch it cross the solar system, we feel that we are witnessing something bigger than ourselves, a reminder that the universe is alive, dynamic, and full of surprises. When we talk about 3I Atlas, we cannot help but think about the ephemeral nature of its visit. It is here for a brief period of time, and soon it will continue on its way to distant regions of the galaxy. That raises an inevitable question. What would happen if we could intercept this visitor? What would happen if humanity had the ability to send a probe to study an interstellar object up close as it crosses our solar system? The idea is not as far-fetched as it seems. In fact, space agencies like NASA and ESA have already considered projects of this type. One of the most mentioned is the proposal for a mission called Comet Interceptor. This mission, still in development, seeks to position a spacecraft at a strategic point in space, ready to launch towards any newly discovered comet or interstellar visitor. The plan is that instead of designing a mission for a specific object, the spacecraft will wait patiently until an interesting candidate appears and then perform the interception. Atlas would be a perfect target for a mission of that class. Imagining a mission to Atlas invites us to reflect on what we could discover. The first thing would be to analyze its surface up close. From Earth, we see it as a luminous point with a diffuse coma and a changing tail. But a nearby spacecraft could photograph its nucleus, reveal its shape, its texture, and its fractures. Is it a compact rock? Or is it a conglomerate of icy fragments barely held together by its weak gravity? Every detail of its appearance would tell us a lot about its origin. The next step would be to directly analyze its composition. A probe equipped with spectrometers could accurately measure the gases it emits, confirm the abundance of carbon dioxide, and look for more complex organic molecules. It could even detect amino acids or other precursor compounds of life. Having that information would be like opening a window to another solar system. We would not be imagining what its formation environment might have been like. We would be measuring it with instruments designed to answer those questions. Small secondary probes could also be launched to pass through its coma and take dust samples. Those particles, captured in special compartments, could be analyzed in space or, in the best of cases, brought back to Earth. Having fragments of an interstellar comet in terrestrial laboratories would be an unprecedented achievement. It would be the first time that humanity would have in its hands material that was formed around another star. That fact alone would justify the effort. Another fascinating dimension would be to study its dynamics. A nearby spacecraft could accurately measure how it rotates, how it reacts to the solar wind, and how its tail changes over time. That data would not only help us understand Atlas, but also prepare for future missions to interstellar objects. Knowing how volatile they are, how stable or unstable their surfaces are, is essential for any long-term plan. Of course, intercepting an object like Atlas is not easy. Its speed, of more than 60 kilometers per second, makes reaching it a huge challenge. It requires very precise orbital calculations and advanced propulsion technology. In addition, its discovery was relatively recent, which leaves little room for preparation. Even so, every new interstellar visitor we detect fuels the urgency to be ready. We may not be able to intercept Atlas, but its anomalies are a reminder of why we must prepare. The next visitor could arrive in a decade or a century, and perhaps be even more interesting. Beyond the technical feasibility, there is an inspiring aspect. A mission to Atlas would symbolize humanity's leap towards direct contact with other stellar systems. Until now, our physical reach is limited to the planets and bodies of our own solar system. We have sent probes to Mars, to Jupiter, to Saturn, even beyond, into interstellar space. But we have not yet touched anything that comes from outside. Achieving that would be like shaking hands with a visitor from another star. A gesture of cosmic encounter that would mark a before and after in our scientific and cultural history. There are those who even imagine a more daring scenario, that in the future, with more advanced technologies, we could follow these objects during their interstellar journey. Instead of simply intercepting them as they pass, we would send ships capable of accompanying them for decades or centuries, traveling with them as traveling companions. In this way, we would learn not only about their structure and composition, but also about the conditions of the deep space they traverse. It would be like sending human explorers to the trade routes of the galaxy, although in this case, the guides would be icy rocks. In terms of planetary defense, a mission of this type would also have benefits. Understanding how an interstellar comet behaves would give us clues to deal with possible future threats. Although Atlas does not represent an impact risk, learning from it prepares us for scenarios in which another object does. Every piece of data on how these rocks interact with the sun and the solar wind increases our ability to predict their trajectories and, if necessary, deflect a dangerous body. Finally, there is the cultural impact. A mission to Atlas would not only be a scientific event, it would be a symbol of global unity. Just as the Apollo missions inspired millions of people around the world, intercepting an interstellar traveler would be a shared feat. It would represent humanity's ability to look beyond its immediate problems and work together to understand its place in the universe. In a world full of divisions, an achievement of that magnitude would remind us that, after all, we all inhabit the same planet under the same sky. Thus, imagining an interception of Atlas is more than a technical exercise. It is a reflection of our aspirations as a species. We want to know where we come from, what is out there, and if we are alone. We want to reach what moves beyond our reach, because every time we do, we expand the limits of what is possible. Atlas will pass and be lost in the darkness of the galaxy, But its legacy can be much more lasting if it drives us to prepare for the next visitor. Science is concerned with measuring, calculating, and explaining. But there is something that transcends numbers every time an object like 3I Atlas appears in our skies. Beyond the data, its visit inspires us, awakens collective emotions, and connects us with questions that have no easy answers. In this block, we will reflect on the cultural, philosophical, and even spiritual messages that humanity projects onto this interstellar visitor. As if in its fleeting crossing through our neighborhood, something deeper about ourselves is reflected. Throughout history, comets have been seen as omens. In ancient times, when their physical nature was not understood, they were interpreted as divine signs. They could announce wars, plagues, or changes of power. Kings and priests looked at the sky with fear when a comet crossed the firmament, convinced that it brought a hidden message. Today, we know that they are nothing more than bodies of ice and dust illuminated by the sun. However, the echo of those interpretations is still alive. When it was announced that Atlas was an interstellar object, thousands of people on the internet commented that it must be a sign, a reminder that we are not alone, or that great changes are coming. Although science does not support these ideas, it is inevitable that they arise. Philosophy also finds fertile ground in a visitor like Atlas. Its interstellar character reminds us that we are not the center of the universe. It is easy to forget in our daily routine that we live on a tiny planet orbiting a common star. But the arrival of an object from another star puts us back in perspective. It tells us that we belong to a dynamic and vast cosmos, where what happens in one stellar system can, millions of years later, have consequences in another. From this perspective, Atlas is not just a comet. It is tangible proof of the interconnectedness of the galaxy. Religion and spirituality have also found symbols in this type of phenomenon. For some people, the visit of Atlas is seen as a reminder of the ephemeral nature of life, of how small human beings are in the face of immensity. Others interpret it as a sign of hope, a message that the universe is alive and in motion, and that there is always something new to discover. In forums and spiritual communities, meditations and reflections inspired by Atlas have been shared, as if its journey could teach us something about our own. Popular culture, for its part, is not slow to appropriate these events. Since it was detected, Atlas has inspired illustrations, songs, and even science fiction stories. Writers have imagined that sleeping beings travel inside it, or that its nucleus hides lost technology. Artists represent it as a cosmic eye that observes us, or as a starship that crosses the oceans of space. Although none of this has a scientific basis, it shows how celestial phenomena continue to feed human creativity. Atlas, in that sense, becomes a canvas where we project our dreams and fears. There is also an existential aspect. Knowing that Atlas will never return, that it is a unique visitor, forces us to reflect on the fleetingness of opportunities. It is a mirror of life itself, brief, unrepeatable encounters that we must take advantage of while they last. In talks and popular science articles, some communicators have highlighted that metaphor. Atlas reminds us that nothing is eternal, that everything that comes into our lives continues on its way, and that the true value is in contemplating and learning during the brief crossing. On a more practical level, its passage also sparks debates about the destiny of humanity. Some contemporary philosophers have pointed out that if we can detect and study objects from other stars, perhaps one day we can also travel to them. Atlas symbolizes that possibility. Contact, although fleeting, with something that comes from elsewhere. It inspires us to imagine a future in which we are the ones who cross the galaxy as interstellar visitors in distant systems. It is interesting to note how different generations perceive it in different ways. For the youngest, Atlas is a viral phenomenon, news that circulates on social networks and that sparks memes and theories. For adults, it is a reminder that science is advancing and that the universe always holds surprises. For the elderly, perhaps it evokes memories of how comets were previously seen as signs of destiny. This variety of interpretations reveals the cultural richness that these phenomena generate. Even in science, there is sometimes an almost poetic tone. Some astronomers have described Atlas as a message in a bottle launched from another star. Others call it a lonely traveler or herald of the unknown. Although these phrases are not part of technical language, they show that even scientists, accustomed to precision, are not immune to wonder. Because in the end, beyond the numbers, there is a human being looking through the telescope, aware that they are witnessing something unique. Atlas also highlights our need to seek meaning. Faced with the inexplicable, we invent stories. Faced with the fleeting, we build symbols. And although we know that it is only an interstellar comet, we cannot help but wonder what its passage tells us. This need to find meaning in the heavens is as old as humanity. What changes is the way of expressing it. Yesterday, it was myths and omens. Today, it is speculation about panspermia or extraterrestrial life. But the root is the same, the desire to understand and to feel part of a larger story. In short, Atlas is not only an astronomical phenomenon, it is also a cultural phenomenon. It inspires art, provokes philosophical debates, feeds spirituality, and ignites the popular imagination. Its fleeting visit reminds us that the universe is not a static stage, but a constantly moving ocean where unknown ships cross our waters from time to time. And every time they do, they leave us not only with scientific data, but also with questions, metaphors, and dreams. The visit of 3I Atlas is not only a phenomenon that awakens wonder in the general public. It has also generated a global scientific mobilization, as has rarely been seen. Astronomers know that this type of event is unrepeatable. When an interstellar object crosses our solar system, we have only a few months to observe it before it is lost in the immensity. Therefore, the international community has worked in a coordinated manner to record every detail of its passage. The process began with the official announcement of its discovery by the Atlas system in Hawaii. In a matter of hours, observatories in different countries pointed their telescopes at the newly identified object. In Europe, South America, Asia, and Oceania, astronomers made confirmation observations to determine its orbit with greater accuracy. The calculation of trajectories requires measurements from different points on the planet. In this way, the hyperbolic curve that confirms its interstellar origin can be precisely traced. Once its nature was assured, the priority was to coordinate the follow-up. The International Astronomical Union and the Minor Planet Center were in charge of collecting and centralizing the data. Each observatory, large or small, sent its reports to be incorporated into a common record. This included measurements of brightness, spectra of its composition, and details of its tail and coma. The result was a shared database that grew day by day, like a collective diary of the passage of Atlas. The coordination also involved space telescopes. The Hubble and the James Webb, for example, were programmed to observe the visitor. These instruments have the advantage of not suffering from the distortion of the Earth's atmosphere, which allows for sharper images and clearer spectra. In parallel, infrared observatories, such as the Spitzer before its retirement, or the Neowise, provided information about its temperature and thermal emission. Each range of the electromagnetic spectrum revealed a different aspect of the comet. Amateur astronomers also played a key role. Thanks to their more modest telescopes, many of them were able to provide regular observations that complemented those of the large observatories. In specialized forums, images, brightness graphs, and activity reports were shared. Some amateurs, equipped with high-sensitivity CCD cameras, even managed to detect subtle changes in the shape of Atlas's tail. This type of observation, repeated night after night, is valuable for understanding how the object interacts with the solar wind. The collective work not only sought to describe Atlas, but also to take advantage of it as a natural laboratory. By analyzing it, scientists could test theories about the formation of comets, the evolution of planetary systems, and interstellar dynamics. Each piece of data collected served not only to understand this visitor, but also to prepare for future encounters. Science advances by accumulating experiences, and each interstellar object detected becomes a key piece of that learning. One of the most interesting aspects was the interdisciplinary collaboration. Not only astronomers participated, but also chemists, plasma physicists, and experts in orbital dynamics. Chemists analyzed the spectra to identify molecules in the coma. Plasma physicists studied how the solar wind affected its tail. Dynamics specialists calculated its future trajectory and estimated how long it would remain visible. This sum of efforts generated a more complete vision, where each discipline contributed its perspective. The collaboration also extended to outreach. Universities, museums, and science centers organized talks and live broadcasts to show the public how Atlas was being studied. On digital platforms, animations of its orbit, comparisons with Oumuamua and Borisov, and simple explanations of why its nature was so special were shared. This interaction brought science closer to millions of people and showed that astronomy is not an isolated effort, but a collective enterprise in which we can all participate in some way. The fact that Atlas coincided with other outstanding objects in September made the attention even greater. It was not just an interstellar visitor. It was part of a month full of cosmic activity. This generated an atmosphere of urgency and enthusiasm in the scientific community. It was known that every clear night, every hour of observation had to be taken advantage of. Many researchers described this period as a scientific marathon, in which fatigue took a back seat to the historical opportunity. In addition, the data collected was not kept under lock and key. Much of the information was shared in public repositories so that any researcher in the world could access it. This transparency allowed even small teams, without large budgets, to contribute with their own analyses. The spirit was clear. Atlas belongs to everyone, and its study should be a global effort. Even improvised proposals for possible interception missions emerged. Although there was no time to prepare a ship to reach it, some groups discussed the idea of redesigning ongoing missions or taking advantage of probes already in operation. Although these ideas did not materialize, they show how Atlas aroused not only curiosity, but also scientific ambition. It was a reminder that we must be ready to act quickly the next time an interstellar visitor crosses our path. In short, the passage of 3I Atlas has been much more than an astronomical phenomenon. It has been an exercise in international cooperation, a demonstration of how humanity can unite to observe and understand a shared mystery. Each telescope, each computer, and each observer, from the most sophisticated to the most humble, contributed to a common story. And although the visitor will continue on its way into the darkness of the galaxy, the data, images, and knowledge it leaves behind will remain with us forever. The passage of 3I Atlas is not only a unique spectacle for this generation, it is also a lesson for the future of science. Every detail observed, every anomaly detected, and every piece of data shared become a legacy that prepares us for the next interstellar visitors. Because the truth is that if we have found 3 in just a few years, it is very likely that there are many more crossing the galaxy waiting to be detected. In this block, we will reflect on what Atlas teaches us and how we can take advantage of it to improve our preparation. The first great lesson is the importance of constant surveillance of the sky. Atlas was discovered thanks to an alert system designed to detect asteroids that could pose an impact risk. Its discovery confirms that the best way to find interstellar objects is simply to observe with patience and continuity. This implies continuing to invest in automatic telescopes capable of covering large areas of the firmament every night. The more eyes we have pointing at the sky, the more likely we are to detect fleeting visitors like this one. The second lesson is that we need speed of reaction. Atlas was identified with enough anticipation to organize global observations, but there was no time to prepare a space mission to intercept it. If we want to study future interstellar objects up close, we must have probes ready, waiting at strategic points. That is the logic behind projects like Comet Interceptor. It is not about reacting when an object appears, but about being prepared beforehand. Atlas reminds us that opportunity can knock at any moment, and that we must have the tools ready to seize it. The third lesson has to do with cooperation. No observatory, by itself, could have recorded all the information that was obtained about Atlas. It was the coordinated work of hundreds of institutions that allowed its trajectory to be reconstructed and its characteristics studied. That dynamic shows us the way forward. In the future, every time a new visitor appears, we will need a global response. It will not be an achievement of a country or an agency. It will be a collective effort of all humanity. The fourth lesson points to interdisciplinarity. Atlas is not only of interest to astronomers. Its chemical anomalies are relevant to chemists. Its dynamic behavior interests plasma physicists, and its possible role as a carrier of organic compounds intrigues biologists. The future of these studies is not in the hands of a single discipline, but in the collaboration between many. Each interstellar visitor will be an opportunity to connect branches of knowledge that, at first glance, seem distant. The fifth lesson is more philosophical. Atlas reminds us of how brief our observation time is. Just a few months of data versus millions of years of interstellar travel. That disproportion teaches us humility. It shows us that we are just fleeting witnesses of a much greater journey. And at the same time, it invites us to seize every moment. In science, as in life, unique opportunities require full attention. They are also practical lessons for technology. Observing such a fast and distant object requires more sensitive telescopes, more powerful algorithms, and faster communication networks. Every limitation faced with Atlas is an incentive to improve our tools. In the future, we may be able to detect even more distant visitors, or even predict their arrival decades in advance. That would give us the necessary margin to design specific missions and plan direct encounters. Another fundamental learning is the importance of education and outreach. Atlas aroused the curiosity of the public, and that is valuable. Every child who heard about an interstellar comet, every person who saw an image on the internet, is someone who now has a stronger connection with science. Outreach is not an adornment. It is an essential part of the legacy of events like this. If we can get new generations interested in astronomy thanks to Atlas, we will have gained much more than data. Finally, Atlas leaves us a lesson about our relationship with the universe. It shows us that we are not isolated, that our solar system is part of a constant flow of matter that travels the galaxy. It teaches us that what happens out there can reach here, and that we too could, one day, send fragments of our world to other systems. Its passage is a reminder that we are part of something bigger, a cosmic network that connects stars, planets, and anonymous travelers in the same fabric. The future of interstellar astronomy will be built on these lessons. Perhaps the next visitor will be brighter, or stranger, or even closer. Perhaps it will bring with it answers to questions that today seem impossible. Or maybe, like Atlas, it will leave us with more enigmas than certainties. In any case, we will be better prepared thanks to the accumulated experience. 3i Atlas will go, but its footprint will remain in our databases, in our photographs, and above all, in our collective memory. Its visit has been a dress rehearsal for the next encounters, and each rehearsal brings us a little closer to being ready for the great discovery. The day when we not only detect an interstellar object, but we manage to touch it, study it up close, and understand it in all its dimension. Thus, the legacy of Atlas is not measured only in what we learned from it, but in what it drives us to seek in the future. It leaves us with open questions, pushes us to improve, and reminds us that the universe is much more dynamic than we usually think. That is, perhaps, its greatest teaching. We come to the end of this journey, a narrative journey that took us through an extraordinary month in the sky. September of 2025 will be marked as a period in which our planet was surrounded by diverse visitors. Large and small asteroids, a newly discovered comet, and an interstellar traveler that is already part of the history of astronomy. Together, they showed us that the universe is never static, that it is always in motion, and that, although we often forget it, our planet is part of a cosmic choreography of unimaginable magnitudes. Let's think about FA-22, the asteroid hundreds of meters across that passed close by and reminded us of the importance of planetary defense. A reminder that the sky is not only a stage of beauty, it can also be a space of risks. Its dimensions made us reflect on how fragile our civilization can be in the face of external forces. It was not an immediate threat, but it was a warning that we must be vigilant, prepared, and united in the study of our celestial environment. Now let's remember RJ2, the small visitor of just a few meters. Apparently harmless, but just as revealing. Its passage reminded us that the sky constantly receives rocks that burn up in the atmosphere, generating luminous spectacles. An everyday phenomenon that we almost never see, but that happens every day. RJ2 was a reminder of how alive the cosmos is, of the constant dance of smaller fragments that cross space like sparks in a bonfire. Then appeared C-2025 R2 SWAN, the new comet that arrived as a surprise. Discovered almost by accident, it showed us that the universe still holds secrets waiting to be revealed. Its greenish glow, its incipient tail, and its promise of a greater spectacle in October made thousands of people look up to the sky with expectation. SWAN reminded us that astronomy is not only calculation and prediction, it is also wonder and discovery. Each comet that appears is an invitation to stop, look, and feel that we are part of something immense. And of course, there is 3i Atlas, the undisputed protagonist, an interstellar traveler who visited us from distant regions, bringing with it a mystery that we have not yet fully deciphered. Its atypical composition, its chemical anomalies, and its rotational stability make it a unique object. But beyond the data, Atlas leaves us with a profound lesson. It reminds us that we are not isolated, that the galaxy is a dynamic place where fragments from other systems can cross our path. It tells us that we are part of a cosmic network much larger than we can comprehend. This month, with its multiple visitors, taught us several things. It showed us that science is a collective effort in which professionals and amateurs, giant telescopes, and homemade cameras participate. It taught us that every object, large or small, has something to tell us. FA-22 speaks to us of risks, RJ2 of the everyday, SWAN of unexpected beauty, and Atlas of cosmic mystery. Together, they form a chorus of celestial voices that remind us of how much we have left to learn. It also taught us to look to the future. If we want to make the most of the arrival of these visitors, we must be prepared. Ready with more sensitive telescopes, with faster algorithms, with probes that can intercept an object in its fleeting passage. Atlas, in particular, showed us that these opportunities do not repeat themselves. If we let it go without learning everything possible, we will have lost a unique window to another stellar system. But beyond science and technology, this month gave us something more subtle. It gave us a reminder of our smallness, and at the same time of our greatness. Smallness, because we are tiny in the face of asteroids, comets, and interstellar travelers. Greatness, because we are capable of detecting them, of studying them, and of reflecting on them. Greatness, because we can transform a point of light in the sky into knowledge, into poetry, and into culture. In the silence of the night, as Atlas crosses the sky, we can imagine its journey, millions of years traveling the interstellar void, perhaps ejected from a system that once had planets like ours, crossing clouds of dust, dark regions, fields of stars. And for a very brief instant on the cosmic scale, it passes through our neighborhood. We, a young species on a blue planet, look at it, study it, and remember it. It is an encounter between two stories, that of the traveler and ours. That encounter invites us to think about our own trajectory. Like Atlas, we are also travelers, although limited to our solar system for now. Perhaps one day we will be able to leave, cross to other stars, and become interstellar visitors. Perhaps then, in another distant world, someone will look up at the sky and see us pass by as we see Atlas today. In the meantime, the only thing we can do is learn, prepare, and continue observing. Every object that passes is a chapter of a larger book that we are just beginning to read. A book written in the stars, in the icy rocks, and in the fragments that travel through the galaxy. Atlas is a bright page of that story, a page that will remain in the memory of our generation. Thus concludes this narrative journey, not with a definitive answer, because the universe rarely offers certainties, but with an invitation. An invitation to continue looking at the sky, to continue asking questions, to continue marveling. Because in every comet, in every asteroid, in every interstellar visitor, there is a story to tell. And in telling it, in listening to it, we also discover ourselves.